Okay, welcome to another video. Today we're doing some probability, and the question is, let x and y be ID standard normal variables. What is the probability y is greater than 3x? And so, okay, first, what does it mean to be ID standard normal? It means x has distribution normal on 0, 1, with mean 0 and variance 1, and y is normal with mean 0 and variance 1. And so we want the probability that y is bigger than 3x. So before one starts trying to, write down, probability density functions, blah, blah, these things, we should try to see if we can manipulate this somehow. And so the easiest thing to do is to just move everything over to one side. And now we have to understand this probability. But if you remember, sums of normal variables are normal. And in particular, y minus 3x is normal with the same mean and variance given by, well, variance of ax plus, or in this case, let's do it this way, minus bx is a squared variance of y plus b squared variance of x minus 2ab covariance of y and x. Since they're independent, we know that this term is 0, although the converse would not be true. And so in other words, the variance of this thing, or y minus 3x, is just 1 squared plus 3 squared, which is 10. But of course, once we know that the mean is centered at 0, we can answer this, because the probability that y minus 3x is greater than 0 is 1/2, since y minus 3x is normally distributed on 0 to 10. And normal distributions have the property that half their mass is centered on either side of the mean. Okay, so that's the answer for this, which might be kind of counterintuitive depending on how you think about these things. Part B of the question is, so what if you already know x is bigger than 0? Then what can you say about this probability? So for this one, we're going to need to use more than just the shape of y minus 3x. But we can also solve this directly by thinking about the joint PDF of x and y and what kind of shape it has. And so an important fact is that this joint PDF is radially symmetric, meaning if you kind of plot what it looks like, and maybe you had some level sets and kind of have these circles like this. And so really you should think about this data as being completely circular. That's where the radial symmetry comes in. But basically in 3 dimensions, it kind of looks like a bell curve from every side you see it at. So I'll try to draw it kind of in 3 dimensions. Maybe look something like this. And then you have more here, etc. And so that's what the distribution looks like. And so if you want to figure out the probability that y is bigger than 3x, given that x is greater than 0, you can use a picture. So we know that the data is Or in fact, maybe I'll draw it as a circle instead of like a box plot to emphasize the shape. This is kind of what the data looks like. It's definitely more concentrated in the center than around the edges because they're both mean centered at 0. And so the part where x is greater than 0 is the right half of this line. And y is 0 right here. So that's the point 0, 0. And so the probability y is greater than 3x, well, let's draw the line y equals 3x. So maybe y equals 3x looks like this. So that's y equals 3x. And so the probability y is bigger than 3x, given that x is greater than 0, is basically the proportion, it's this area, divided by maybe the whole x greater than 0 part, which I'll put in yellow, including this part. Okay, so probability we want is red region divided by yellow plus red region. So to compute this area, well, it's the same because everything is sort of uniform on these circles. We just have to know the ratio of this angle to the total angle, which we know is the total angle is pi if we're thinking about in radians. And so how do we figure out this angle? Well, the slope of this is 3, which means we rise by 3 and go over by 1. So the tan of this angle is 1, it's like 1 over 3, at least in ratio. So this isn't literally 3, but this is the change. And so this angle is equal to arctan of 1 over 3. And so that is our final answer.